Good afternoon, good evening, everyone. My name is Raghunath Hardy. I'm a senior marketing manager at MPS. So I'm responsible for our automotive compute product line. So this is basically, we specialize in powering the automotive SoC core rails. So today, I will talk about the challenges and opportunities in powering automotive SoCs. So we are talking about we are going to talk about the SoCs that that run the ADAS systems or high-end infotainment systems, high-performance compute systems in automotive, and what kind of power management solutions they would require, and what are the products that are suitable for those kind of applications. So we'll cover those today. So talking about agenda, so I'll first discuss the problems faced by today's mobility, and then how we can solve, or how the automotive industry is going to solve those problems faced by mobility today. And for that, I will briefly discuss the market size for ADAS or autonomous vehicles in the future. And in terms of architecture, automotive is going through a digital transformation. So I'll show some of the details about the evolution of automotive computing. And powering the SoC core rails, there are traditional ways of powering them with the discrete components. I will talk about that. And then what are the available advanced power management solutions that can be leveraged from non-automotive applications. So I'll show some of those details as well. And then at the end, just as an example, I will show a couple of products from MPS side as well. So if you look at the challenges faced by today's mobility, we all know that we all know that world's population is growing, and a lot of urbanization is happening. If you take some statistics, today 55% of the global population lives in urban areas, and we all know that it is only going to go up, increase. And because of that, the infrastructure mobility is suffering congestions and accidents. And on the other side of the spectrum, if you look in developing countries, still there is population that doesn't have proper access to mobility. So because of that, those economies in developing countries, the economy is suffering due to lack of access to mobility. So congestion, we know that people spend a lot of hours in commuting to work or other places. So because of that, the productivity is lost, and the other health consequences as well, right? And accidents, we know that billions of dollars lost because of accidents, and there are statistics out there showing a lot of impact to the economy in developing countries because of lack of access to mobility. So the industry today, automotive industry, by enabling ADAS systems and autonomous vehicles in the future, and once the autonomous driving technology is available, robo taxis and shared mobility is going to enable a convenient, safe, and economic mobility to solve today's problems faced by the mobility infrastructure. So given that context, we already see that the ADAS market is growing at a breakneck pace. If you see the graph on the right-hand side here, the ADAS market is going to grow to $90 billion industry by 2030, growing at a fast 19% CAGR. So the catalysts are increasing focus on safety, not only from consumer side, but also from the government's mandating use of advanced safety features. This is going to accelerate the adoption of ADAS systems in the future going forward. And also from consumer side, the comfort and affordability is increasing. Because of that, there is rising demand for comfort and luxury in the vehicles. So what I mean by comfort and luxury is like high-end infotainment systems, rear seat entertainment systems, connectivity, and all those things are being demanded by the consumers, the future purchasers of the vehicles. And given this growth in the market, there are heavy investments happening in technology and infrastructure by companies. So like, for example, the companies that develop sensors for ADAS systems, or SoCs for ADAS systems, and other software and hardware technologies required by ADAS systems. So a lot of investment and technology advancements are happening in this area to support the future mobility. So if you dig a little bit deeper here, so the SoCs that run the ADAS systems are IVI, or in-vehicle infotainment systems, and specifically talking about ADAS here. So today we are on the bottom left corner of this picture here. We are at feet off today. Uh, because of this adaptive cruise control, those type of features, we are at feet off, and then we are progressing towards moving towards hands off and eyes off, and eventually mind off when we are driving the vehicles, right? So the SAE levels for autonomy, they are categorized. There are 6 categories: L0 to L5. L0 being no ADAS features, L5 being the robotaxi, right? The fully autonomous vehicles, even without the steering wheel in the car. So the important because of this transformation, or this adoption of ADAS systems going all the way up to L5, it requires a lot of computing. So the automotive is becoming a servers on wheels to enable the highest level of autonomy, L5, in the future. But if you look at the SoCs that run these ADAS systems for feet off, like L1 to L2, in that range of autonomy, typically the SoCs that run at 30 tops. Tops is tera operations per second, and then for L5 all the way up to L5, 1,000 tops, or even higher to enable L5. So what this means is the rise in tops, tera operations per second, is that the SoCs, the more and more powerful SoCs, are being implemented in automotive to enable the highest level of autonomy. And these powerful SoCs even will perform a lot of computation required by ADAS, or autonomous vehicle systems. So going one layer down, here I'm showing the evolution of computing architecture. So in the past, it is all distributed architecture, tens of ECUs sprinkled all over the vehicle to take care of the local computational needs in the vehicle. But then it became a domain-based ECUs that more or less 95% or even higher number of vehicles on the road today use the domain ECUs today. But in the future, as we are going to adapt more and more of ADAS, or even advanced ADAS, in the future, the architecture will move towards a central computer architecture, and everything, the process in the computing processing will be centralized and run by the central computer, whether it is for ADAS or infotainment or high performance compute in the vehicle. So these central computers are run by powerful SoCs, as I mentioned before. So because of that, the central computer SoC will be 44% of the total processor spend in a vehicle by 2030. So in the future, like everything will be, all the computing will be centered around this SoCs. That SoC being so powerful, it will, for example, if $100 are spent on the processors for automotive, $44 of that spend will go towards the central computer SoC. And because of that, the SoC market for central computers will be $30 billion by 2030, growing at 26% CAGR. So now we talked about the transformation, the architecture evolution. So we know now that more and more powerful SoCs will be used in the future for ADAS systems. So how do we power these SoCs? So let's take a look. So there are traditional ways of implementing it using discrete components. So that as an industry, we are all familiar with analog PWM controllers and MOSFETs. And because of the analog controllers, they require the traditional feedback loop compensation, so on and so forth. And then for driving the discrete FETs, the high side FET, low side FET being discrete FETs, they need gate driver IC in between the controller and the MOSFETs to drive them. And for current sense and temp sense, it is done discretely. For current sensing, we are all familiar with DCR current sensing the current through the inductor, but we know that it is not accurate. It has a lot of variations due to temperature and so on and so forth. So this is the traditional way of implementing it here. I'm showing an SoC, let us say, as an example, that SoC requires two high current rails, and the rail 1 is 100 amps and rail 2 is 60 amps. So if we implement this using a traditional solution with analog controller and discrete MOSFETs, there are a bunch of components to implement this solution. It requires large PCB size, and because of too many components here, they are complex to design and very hard to optimize. So this takes a lot of design effort. So the design cycles are longer, and the amount of R&D dollars spent is also huge. So do we have any options to implement a better solution for this? Yes, there is. Instead of the analog controllers, we can use digital multi-phase controllers, and instead of using the discrete MOSFETs, gate driver IC, current sensing, temp sensing, instead of using that cumbersome solution, we can use a Driver-MOS or Doctor-MOS components here. So compared to the previous slide, here it is a very simple solution to implement. The same two high current rails, 100 amps and 60 amps here, and we see very few components, just 5 components here. In terms of silicon, only 5 components, only 2 types of components here, a controller and Driver-MOS here. There is no discrete components around them. So these enable high level of integration, higher power density, and the digital controllers offer a lot of flexibility, programmability. So they are easier to design with, easier to optimize. All in all, they will enable a shorter design cycle, which is R&D dollars are less R&D dollars with these solutions. So if we draw some parallels with other industries, for example, if you take a PC power architecture, so the PC CPUs, they also have high current rails for CPU, GPU, or other rails. So for PCs, there is a 19-volt adapter or a battery that power the system, and they take the 20 volts coming in, and a digital multi-phase controller and the Driver-MOS products are powering the high current rails in the PC architecture already. And then for other rails, discrete point of load converters can be used. So PC industry has made this transformation more or less already, at least on the high-end PC systems. And if we draw parallel to a server application, we see here servers, they have a 12-volt bus coming in. So for servers, they can use 16-volt rated Driver-MOS power stages to power the CPU, GPU rails, or any other like memory or any other rail, any other high current rails. So in servers also, these kind of solutions, digital multi-phase controllers with paired with the Driver-MOS products is already being used for a few generations. Now, if you look at the automotive SoC architecture, if you look at you can divide the power architecture into two categories: high current rails and low current rails. So as an example, I'm just showing here, the high current rails are typically like 15 amps or higher. Those are typically SoC core rails that power the CPU or GPU inside the SoC. So if you compare it with the PC or server, automotive is also looking, the power architecture for automotive is also very similar: high current core rails and low current power rails for the rest of the system here. So since the PC industry and server industry is already using digital multi-phase controllers paired with Driver-MOS solutions, they can be used for automotive SoCs as well to enable high efficiency, fast transient response required by the SoC core rails, and dynamic voltage and frequency scaling is required for core rails, and some real-time monitoring and reporting, all these features, right? So here I'm summarizing. So the focus of this presentation is the SoC core rails. So whatever the industry is, whether it is automotive or PC or servers, the core power, SoC core power has these requirements common between the industries: high efficiency, high power density, fast transient response, dynamic voltage and frequency scaling. This is because the SoC core rails will have very stringent low transient requirements. The SoC will require a lot of current when it is doing high level of computation, but the rest of the time, the SoC will go to a low power mode to save the power. So because of this, the SoCs exhibit huge, or SoCs demand huge load steps. So the power management solution should be able to support the huge load steps and also the voltage and the frequency scaling. Because these SoC core rails are so critical to the power management system, so the SoC would want to monitor the health of the power management system. So the SoC core rails, the controllers used for SoC core rails will have to implement a digital interface so that it can talk to the SoC to perform different levels of monitoring, reporting, or other functions. And the SoC core rails, during the design, I will show a little bit detail later in the slides. They need a lot of scalability and flexibility also during the design. But in addition to all of this, the automotive SoC, as opposed to the PC or server SoCs, now they have additional requirements for automotive. They have to be AEC-Q qualified because of the harsh working conditions in automotive, high reliability requirements. So AEC-Q qualification is required. And in some systems, functional safety is also required for automotive power solutions. For example, ASIL-D level functional safety. So MPS background in this area is MPS has powered SoCs in PC, server, data center applications for multiple generations. So MPS has a lot of experience, products, and technology that supported PC, server, and data center applications. So MPS is applying that same technology, products, and know-how into powering automotive SoC core rails as well. So MPS is designing grounds up AECQ solutions for SoC core rails, and MPS has the capability to implement the highest level of functional safety, ASIL-D, into the automotive solutions here, whether it is for ADAS, infotainment, or high-performance computing. So let me show a few some more details about the digital controllers here. I'm showing as an example MPQ2977, a digital multi-phase controller. So when I say it is multi-phase controller, so here, for example, this controller is generating two independent output rails, Vout A, Vout B. For each rail, there are two phases are used. One Driver-MOS for one phase here with its inductor, the second Driver-MOS here for another phase to support the Vout A rail. And for Vout B, same here, two Driver-MOS phases to support Vout B. So if you look for external components, right, this is supporting two high current rails with the two phases each. But if you look for external resistors or capacitors around the controller or Driver-MOS, you will find very few components here. That's why I have been saying this is a highly integrated solution that is required by advanced SoCs. The digital controller versus analog, what are the benefits? The digital controller, the compensation is done inside the controller itself. There are no more resistors or capacitors to play with to optimize the loop compensation and so, or any other things, right? It comes with a GUI. I mean, since it is a digital controller, it has non-volatile memory, so that you can reprogram the register settings inside the controller using a GUI during development to optimize the designs. So we use at MPS, we use our proprietary PWM technique. So this PWM technique offers very fast transient response. I have a couple of example transient waveforms later in the presentation, but for SoC core rails, as I explained before, they require huge load steps and very fast transient response. So a specialized PWM technique is required to provide the fast transient response with the fewest capacitors, output capacitors. And this is a multi-phase operation, so they need better current balancing between the phases. So each phase can share the current equally. So our PWM technique that we use offers inherent current balancing between the phases. And because these are digital controllers, a lot of programmability, flexibility, and scalability available, as well as a lot of protection features and monitoring and reporting available from these digital controllers. When it comes to Driver-MOS, MPS, we do have a monolithic Driver-MOS, meaning that the high side FET, low side FET, gate driver IC, current sensing, temp sensing, all of these are implemented on a single piece of silicon in our Driver-MOS that gives the best performance, highest power density, accurate current sensing. With our Driver-MOS, even in AECQ conditions, we can guarantee plus minus 5% current sensing accuracy across line, load, and operating temperature range. And not only accurate current sensing, but since it is a monolithic design, it has very accurate temperature sensing as well. So these are the details about our digital controllers and Driver-MOS products. So let's dig into what kind of power architecture available to power the automotive SoCs. Is it single stage or two stage? What are the differences between them? I can talk about that. But before getting into that, let's just roughly understand what is the figure of merit for a MOSFET. So it is RDS on multiplied by gate charge. So it is the lower, the better for figure of merit here. So if you look at the 25-volt FET versus a 40-volt FET, the figure of merit is 23 for 25 volts FET, and it is getting worse. For 40-volt FET, it is more than doubling to 57. So the voltage rating, we can get better figure of merit, which equals to higher performance with the lower voltage. So let's keep that in mind, and it becomes important here in this architecture here. For very high power SoCs, which eventually, in the future, automotive will use more and more powerful SoCs. So for high power SoC systems, the efficiency is absolutely critical. It is to save power, but also more importantly for thermal management. Higher the efficiency, the better it is for managing the thermals in the system. So with 12-volt battery, if it is a lithium-ion battery, then it has 20-volt max. But if it is a lead-acid battery with kickback voltage on it or load dump requirements, it can go up to, the transients can go up to 36 volts. So if we want to have very high efficiency in the power conversion for SoC core rails, we propose using a 22-volt Driver-MOS with an optional pre-regulator. If a lithium-ion battery, 12-volt battery is used, the maximum is 20 volts, including the transients. So we don't even need this pre-regulator here. So you take the 12-volt battery, use our controllers and Driver-MOS solutions to go to SoC core rails directly in a single power conversion, single stage power conversion, giving you the best efficiency. But if it is a lead-acid battery with the load dump voltage transients going up to 36 volts, we can implement a pre-regulator. So this pre-regulator is basically nothing but a buck controller, a buck converter that can run in bypass mode. So what I mean by that, when the output of this buck pre-regulator can be set at, let us say, 20 volts. During all normal operating conditions, the battery is staying under 20 volts. So at that time, this is in the pre-regulator in a bypass mode, meaning that the high side FET is always on. So you lose the RDS on losses of the high side FET and a series inductor. So the pre-regulator stage gives you higher than 99% efficiency. So for all practical purposes, in all normal operating conditions, it is a single stage power conversion, giving you the highest efficiency required in high power SoC applications. But only during those few milliseconds when the battery voltage exceeds the 20 volts, this buck converter now operates as a buck stage, stepping it down to 20 volts. So only during those few milliseconds you lose the efficiency in the pre-regulator, but all other normal operating conditions, it is a single stage power conversion, giving you the best efficiency. So we propose for high power SoC systems, we propose using a single stage power conversion using 22-volt rated Driver-MOS with an optional pre-regulator. So for that, controller is common, whether it is a single stage power conversion or two-stage power conversion that I will talk about in a minute. The controller is common. So here I will show one example controller to show a little bit more details about the features of the controller, digital controllers here. MPQ 2967 is a ASIL D functional, highest functional safety level controller. It can generate 2 independent output rails, and it has a total of 4 phases. So the beauty of these controllers, the multi-phase controllers, digital multi-phase controllers, is it has a total of 4 phases, but you can configure the phases depending on the current rating of each rail. It can generate two rails. For example, the rail 1, if it requires higher current, you can put 3 phases on it. And for rail 2, you can use only 1 phase, or vice versa. Or if you want to use this controller to generate only one output rail, you can use all 4 phases on it, on a single rail. It can generate one rail, all 4 phases on it. So these kind of multi-phase controllers give a lot of flexibility in terms of scaling the power ratings depending on your needs. Here, so I talked about our PWM, proprietary PWM technique that has very fast transient response to reduce the output capacitors and still have a predictable EMI here. And since these are digital controllers, a lot of flexibility. We talked about that. It has digital interface to talk to SoC for programming and monitoring. And it has, this particular SoC has a PWM WID interface for dynamic voltage scaling. And it has the non-volatile memory. And if you look at the protection features, the SoC core rails are so critical to the system. ADAS systems, so it has a bunch of protection features here, and it has automatic phase shading. So let us say you configured this controller for a 3+1. It is generating 2 rails. The rail 1 has 3 phases on it. Rail 2 has 1 phase. So for rail 1 with 3 phases, when it is operating at full load current, all 3 phases are on. But if the load current is reducing, the controller can detect that and it can start shading the phases. If at full load, all 3 phases are on, working, but if the current is reducing, it can go down to 2 phases. If the current is reducing further, it can go down to 1 phase, and eventually it can get into discontinuous conduction mode also. The reason for this is to optimize the efficiency across the load range. From light load to full load, it will have a flatter looking efficiency curve because of this. And then it has active current balancing between the phases. And this particular controller, it's a 2-rail controller, but each rail has its own enable pin to implement any required power up or power down sequence. So very comprehensive controller, digital multi-phase controller here required by advanced SoCs in automotive. So I'll show one example, Driver-MOS. This 86960 is a 50 amp, 22 volt rated Driver-MOS. It is monolithic. So monolithic design offers, as opposed to a multi-chip solution, multi-chip Driver-MOS solution that you might find in the market. So multi-chip solution, they take the high side FET die, low side FET die, gate driver IC die, all separate dies, and co-package it together with wire bonds running between these 3 separate dies. So as opposed to that, the monolithic Driver-MOS offers very good performance because it doesn't have those wire bonds and other parasitics associated with it, right? So with monolithic Driver-MOS, you can push the frequencies higher. You can still get very good efficiency and very good performance out of them. So this 22 volt Driver-MOS, even though when we say it is 22 volt, but it has a wide operating input range. It can operate down to 3 volts. So in automotive systems, there is a cold crank requirement also. During cold cranks, the battery voltage can dip down to, let us say, 6 volts. And by the time the power battery reaches to the Driver-MOS power stage, it could be 5 volts. But being able to run all the way down to 3 volts, it can cover the cold crank scenarios also in automotive applications with our Driver-MOS with the wide operating input range. So you don't need a pre-boost stage to the Driver-MOS. And yeah, it has it requires a 5 volt input for biasing the Driver-MOS. and it has accurate current sensing, temp sensing, and in addition to the protection features we saw in the digital controller, the Driver-MOS has its own protection features to respond fast to any faults that happen in the system. So this Driver-MOS is available in a 5x6 LGA package. So here I'll show one example here. So we have a design here with the 12-volt input coming from the battery, and output is 0.75 volts and 100 amps thermal design current. But if you look at the load steps, right, it is very fast slew rate, 100 amps per microsecond, a 70 amp load step. If we apply that load step here, and we still have a very stringent transient spec to meet, plus minus 3%. So this solution we implemented using our MPQ 2967 controller with the 4 phases of 86960, but still the total PCB size is less than 1,000 square millimeters. So if it is compared against a traditional analog solution with discrete FETs, discrete gate driver IC and all, so this is a very compact design, 950 square millimeters to implement a 0.75 volts, 100 amp power supply with such stringent voltage transient specs. And this huge conversion ratio in a single stage power conversion, going from battery down to 0.75 sub 1 volt rail, we can still achieve 90% peak efficiency with this solution here. So we talked about single stage power conversion going straight from battery down to SoC core rails. But for medium to low power SoC applications, sometimes you might find a cheaper, you might be able to implement a cheaper solution with the 2-stage power conversion. So we have that also covered with the 6-volt rated Driver-MOS power stages. So from the same 12-volt battery, or in the future when the battery, automotive battery goes to 48-volt architecture, you would have a first stage conversion here, stepping the battery voltage down to an intermediate bus, 5 volts or 3.3 volt intermediate bus. Here, you can use a 6-volt rated Driver-MOS optimized to run off of 5 volt or 3.3 volt intermediate bus going down to SoC core rails. So in 2-stage architecture versus single stage high power applications, you need high efficiency is the most critical parameter there. So you are better off implementing a single stage power conversion. But for medium to low power SoC applications, with the 2-stage, efficiency is as critical, so you can sacrifice a little bit of efficiency, but by implementing a 2-stage power conversion, you can push the second stage frequency higher, let us say, up to 2 megahertz as an example. So higher frequency means lower number of output capacitors and smaller inductors. So all in all, you could have a low cost implementation with the 2-stage power conversion here. So that's why MPS specifically when we talk about us, we have both 22-volt rated Driver-MOS for single stage power conversion and 6-volt rated Driver-MOS for 2-stage power conversion. As an example, MPQ 86760, it is a 45 amp Driver-MOS here in 4x5, very compact, small 4x5 QFN package. So it is similar. The underlying technology, monolithic Driver-MOS technology, is similar to our 22-volt Driver-MOS I showed earlier. But this is at 6-volt rating for 2-stage power conversion. Right here, I show an example design. Here we are going from a 5-volt intermediate bus down to 0.7 volts. But this time around, there is 150 amps max peak current, 90 amps thermal design current, And if you look at the load step, 70 amp load step at 100 amps per microsecond slew rate. So we are switching, since it's two-stage power conversion running off of 5 volt, so we can switch, push the frequency higher to 2 megahertz. Even at 2 megahertz switching frequency, we can still achieve 88% peak efficiency. And for such a high current rail, we can still have a compact solution, about 750 square millimeters here. So this design here, we are meeting plus minus 5% transient spec here, even with such a huge load step, 70 amp load step at fast slew rate. Okay. So now a couple of slides here to talk about what kind of support we provide. Since these are digital controllers, you can have a GUI that is provided with the parts or evaluation boards. The GUI can be plugged into the evaluation board, and on the other end, it can plug to your PC. So PC, you open up this GUI, and there are all the register value settings are available here. So when you're during the development, you can program or reprogram these digital controllers for your needs, and you can tweak them as needed to optimize the design. So it helps to reduce the design time using this GUI, and of course, MPS can support you as well in programming or providing training for how to use these GUIs and so on and so forth. So in terms of evaluation boards, I just want to show a couple of examples here. This on the left side, you see MPQ296, a two-rail four-phase controller that I talked about earlier. And then this Driver-MOS is configured as a 3+1. So this is an example EVB here. And then on the right side, you see this is 22-volt Driver-MOS EVB on the left side here. On the right side, you see the EVB with the 6-volt rated Driver-MOS here with the 2977 controller configured as 4+2 here. So the SoC core rails, they need special attention. So MPS, we not only provide EVBs and so, but we can also support you doing paper analysis, provide paper design, PCB area, PCB size analysis, all the other analysis that goes with the designing the core rails. So we provide very strong support, application support to design these critical rails for automotive SoCs. All right, so let's quickly review the summary. So given the adoption of ADAS and eventually the autonomous vehicles, robot taxis, to enable all of these to solve today's mobility, today's challenges faced by mobility. So the automotive industry is undergoing a digital transformation to solve these problems. And because of adoption of ADAS or AV, the market is skyrocketing with the safety and comfort in mind. So at the center of all of this, there's a powerful SoC that runs the central computer to enable the future autonomous vehicles. And the SoCs, these automotive SoCs, specifically their core rails, require advanced power management solutions because of these stringent electrical requirements that I have explained before. So these solutions that I presented to you. They are not new, any exotic solutions. These solutions were used for multiple generations in PC, server, data center applications already. So we are just taking those products, leveraging those products and technology into automotive world as the usage of the powerful SoCs is increasing in automotive. So all in all, MPS is well positioned with a broad portfolio of digital multi-phase controllers and Driver-MOS products to support any SoC core power requirements that you might have in your designing your systems. All right, that concludes my presentation, and now let's open it up to Q&A.
Great. Thank you, Raghu. Now, if anyone has any questions, please use the QA button located at the bottom of the Zoom meeting interface, and we will answer them live. One of our most asked questions is if the session is being recorded. It is being recorded, and it will be sent out to all registrants and posted on our website within the next couple of days. And it looks like we already have a few questions. First one, how will the cost grow over with higher computive power?
Yeah. So on the power management side, yes, as the power is increasing, the power management solution cost will increase as well. But that's the consequence of needing advanced power management solutions.
Great, thank you. Next question, how much load we can connect to the 50 amp Driver-MOS in practical? Can it be full 50 amp or do we need margin?
Yeah, so it depends on your thermal design. Yeah, so the Driver-MOS is rated to support 50 amp continuous current, DC current. But if you have for margin, or if for your, depending on your thermal design, so you could derate it derate it as required, maybe down to 40 amps, or as an example, you can derate it to 40 amps depending on your thermal system design. But the
Great,
parts are designed for 50 amp DC current.
great, thank you. Next question, how can we reduce EMI and switching regulator, which can help reduce the possibility of certification passing issues?
Yeah, there are different ways of implementing, like for example, snubbers is one way of doing it. But also, I mean, when you are designing with our solutions, we can provide the support required to look into the EMI aspect as well.
Great, thank you. Next question, do we need additional heat sink for these digital controllers and Driver-MOS as they are handling higher current?
Yeah, so as an example, some of our customers, they implement liquid cooling. It's not just for the power management solution, but it is for the SoC as well. So for SoC core rails, they sit right next to the SoCs. So the thermal management that is implemented for the SoCs will also be used for the Driver-MOS. But there is no such, I mean, there is no specific requirement, thermal management required for the Driver-MOS itself.
Great, thank you. Next question, will GaN FETs be supported, protection, drive levels, etc.?
I'm sorry, Michaela, could you repeat that question, please?
Yeah, it says, will, and I could be butchering this as well, but will GaN FETs be supported, protection, driver levels, etc.?
Oh, GaN. Yeah, these the Driver-MOS products I have shown in the presentation. They are based on silicon technology. They are not GaN. So there is no special protection requirement for the Driver-MOSes I showed. But the GaN requires a special gate drive protection, but not our Driver-MOS, since these are implemented using the silicon technology.
Great, thank you. I'm not seeing any other questions. If you do have any questions, please type them in. We'll hold here for a few more seconds. If anyone has any last minute questions, we can answer them now. Let's see, we just got another one in. Do you see a move to a battery voltage beyond 48 volt?
No, I don't see battery voltage going beyond 48 volts. So even 48 volt also, there are some EV OEMs, they are making that move. For example, it is a public information that Tesla announced that they will be adopting 48 volts. So from my experience, I think 48 volt will take a while for the rest of the industry to adapt to. But beyond that, I don't see a need to go beyond 48 volt at this time. Even with 48 volt, you can support all the increasing power demand coming from the ADAS systems and infotainment systems and so forth. So 48 volts should be sufficient to reduce the I squared R losses in power distribution and so on and so forth.
Great, thank you. Looks like we have another question that could be related. What are the load dump and cold crank requirements for 48 volt?
Yeah, so based upon my experience so far, I mean, specifically talking about the EV architecture. In EV, there is a high voltage battery already. So for EVs, the 48 volt is generated by stepping the high voltage battery down to 48. So in these scenarios, the 48 volt is distributed throughout the EV vehicle. So they will maintain in a separate 48 volts. For example, today's focus is the ADAS systems, right? So the ADAS box will have its own 48 volt bus. So it is not combined with any other systems, subsystems in the vehicle. So the 48 volt will not have huge voltage transients like the traditional 12 volt battery. So what I see is that the 48 volt probably anywhere between 36 to 60 volts, maybe like another 10 volts transient. So let's say like 36 to 70 volts will be the range of the 48 volt system.
Great, thank you. One more question. Pre-buck converter is option. Will it impact anything on performance for 20 volt?
No. So pre-buck. So obviously, I mean, the pre-buck will take some board space, will have some cost associated with it. But in terms of performance, electrical performance, there should not be any issue. So we have experience. We have implemented such systems. They are in production already, and I don't see any issues. So yeah, careful design must be done with the pre-regulator. So when the battery voltage, and for example, so this pre-regulator has to transition between being in bypass mode to a buck mode, but that can be done. It's not too harsh of a requirement, because the battery, when it is going through its load dump scenario, the battery voltage will increase, but that increases, relatively speaking, at a slower pace, at a slower rate, where the pre-regulator will have enough time to react to the voltage transient to transition from bypass mode to buck mode. That I would design, I would look into that a little bit more carefully, those transitions going from bypass to buck and back from buck to bypass mode. Those transitions, I would design them carefully. I will test them carefully. But other than that, it's a pretty straightforward solution.
Thank you. Again, a couple more questions here. How to design controller for DC to DC converter?
How to design controller? Yeah, so all the solutions that I have showed so far, they are DC to DC conversion. So these are The SoC core rails, they have this fast transient response and some voltage scaling and such things. They make it, those type of requirements make it a little bit more complicated than any other DC-DC. But other than that, these are like standard. Other than that, the design principles are same as DC-DC conversion solutions or implementations.
Thank you. Another question. Does the solution perform well for higher automotive temperature range?
Yeah, so our solution so far, they have up to 150-degree junction temperature. But if beyond that, I don't see any reason to go beyond that. But if there is such a requirement, we can take a closer look at it.
Great, thank you. I'm not seeing any other questions. These were all great questions today. So if you do have any other questions, feel free to quickly type them in and we'll answer them live. Otherwise, thank you for joining us today. We look forward to having you at many future sessions. Oh, and yep, question just came in. Will we share this session PowerPoint? Yes, we will. Once we get the recording posted and sent out to all registrants, the PowerPoint will be included in that. It will just take us a couple days to get that up and running. But yes, PowerPoint will be included. All right, I'm not seeing any more questions. Again, thank you for joining us today and have a good rest of your day.